Optimistic concurrency control is a concurrency control method applied to transactional systems such as relational database management systems and software transactional memory. OCC assumes that multiple transactions can frequently complete without interfering with each other. While running, transactions use data resources without acquiring locks on those resources. Before committing, each transaction verifies that no other transaction has modified the data it has read. If the check reveals conflicting modifications, the committing transaction rolls back and can be restarted. Optimistic concurrency control was first proposed by H.T. Gong. OCC is generally used in environments with low data contention. When conflicts are rare, transactions can complete without the expense of managing locks and without having transactions wait for other transactions' locks to clear, leading to higher throughput than other concurrency control methods. However, if contention for data resources is frequent, the cost of repeatedly restarting transactions hurts performance significantly. It is commonly thought that other concurrency control methods have better performance under these conditions. However, locking-based methods also can deliver poor performance because locking can drastically limit effective concurrency even when deadlocks are avoided. OCC phases, more specifically, OCC transactions involve these phases: begin, record a timestamp marking the transaction's beginning. Modify, read database values, and tentatively write changes. Validate, check whether other transactions have modified data that this transaction has used. This includes transactions that completed after this transaction's start time, and optionally, transactions that are still active at validation time. Commit rollback, if there is no conflict, make all changes take effect. If there is a conflict, resolve it, typically by aborting the transaction, although other resolution schemes are possible. Care must be taken to avoid a toe-tie bug, particularly if this phase and the previous one are not performed as a single atomic operation. Web usage, the stateless nature of HTTP makes locking infeasible for web user interfaces. It's common for a user to start editing a record, then leave without following a cancel or logout link. If locking is used, other users who attempt to edit the same record must wait until the first user's lock times out. HTTP does provide a form of built-in OCC. The GET method returns a new tag for a resource and subsequent puts use the tag value in the if-match headers. While the first put will succeed, the second will not, as the value in if-match is based on the first version of the resource. Some database management systems offer OCC natively, without requiring special application code. For others, the application can implement an OCC layer outside of the database, and avoid waiting or silently overwriting records. In such cases, the form includes a hidden field with the record's original content, a timestamp, a sequence number, or an opaque token. On submit, this is compared against the database. If it differs, the conflict resolution algorithm is invoked. Examples MediaWiki's edit pages use OCC. Bugzilla uses OCC. Edit conflicts are called mid-air collisions. The Ruby on Rails framework has an API for OCC. The Grails framework uses OCC in its default conventions. The GTM database engine uses OCC for managing transactions. Microsoft's Entity Framework has built-in support for OCC based on a binary timestamp value. Mimer SQL is a DBMS that only implements optimistic concurrency control. Google App Engine Data Store uses OCC. The Elasticsearch search engine supports OCC via the version attribute. The MongoDB column-oriented database management system's transaction management scheme is based on OCC. Most implementations of software transactional memory use optimistic locking. Redis provides OCC through watch command. See also: server message block opportunistic locking. References. External links: Kung, H.T. John T. Robinson. On Optimistic Methods for Concurrency Control. ACM Transactions on Database System 6, 213 €226 doi, 10.1145/319566.3195667. Enterprise Java Beans, 3.0, by Bill Burke, Richard Monson-Haefel, Chapter 16. Transactions, Section 16.3.5. Optimistic Locking, Publisher, O'Reilly, Pub Date, May 16, 2006, Print ISBN 0-596-00978-X, Hallman, Andreas. Multi-isolation, Virtues and Limitations. Multi-isolation. 01069 Gskvst 30 per Fahrenheit 301.2, Dresden, Happy Guys Software GBR. Pages 8. Retrieved May 16, 2013.